Howdy, and welcome to our continuing look at triple integrals. This time we'll be looking at cylindrical and spherical coordinates. So without further ado, let's get right into it. This lecture is going to assume that you're already comfortable with iterated integrals in 3 dimensions. So the first thing we're going to do is recall that cylindrical coordinates are going to use polar coordinates and then z. So x and y essentially turn into polar coordinates, and z remains z. So what we have is x equals r cosine theta, y equals r sine theta in the normal way, z equals z. So we might consider something like this shape. So here, not particularly well drawn because it's me drawing it, but this particular shape here is supposed to be something where the height is relatively well described in terms of Cartesian coordinates, but the x and y, the depth and width, if you will, are actually described best as arcs. Maybe you can see this better in the region down here, D. So what happens here, or the x and y are best described actually in polar, essentially. So what might happen here is we say, okay, well, I want to describe z in terms of x and y because that's fine, but then I want to actually deal with x and y in terms of polar, and this would be cylindrical coordinates at its finest. A lot of times we'll use cylindrical coordinates when we're working with, perhaps unsurprisingly, a cylinder. It's something where it's best to think of the x and y plane as polar, and then the z plane as Cartesian, as just strict lengths in the normal sense. So if we make the replacement x equals r cosine theta, y equals r sine theta right away, then z becomes then a function, z equals g sub 2 of xy, or g sub 1 of xy, becomes g sub 2 of r cosine theta, and then r sine theta, or g sub 1 of r cosine theta, r sine theta. And now, instead of dealing with x and y, integrating with respect to x and y, we're integrating with respect to r and theta, and maybe r is between two functions of theta, and theta is just between two constant angles, alpha and beta. So this is what we're working with here. This is the type of thing we're working with, where the region that we project onto in 2 dimensions is best described in polar coordinates. And this is hopefully going to be a relatively simple. This is going to be hopefully relatively simple to solve, because most of the time you're doing the exact same thing you were doing with triple integrals, but then just switching to polar halfway through the problem, or ahead of time. Both work. So what you can do is just convert. You can just go ahead and think of your function as f of r cosine theta, r sine theta, z, and then the dz here is going to stay unchanged, but instead of like dy dx, we have r dr d theta, in the same way that we converted to polar and double integrals. So if this is what we're working with, then it's really just best to see this happen by example. So let's take a look. So we've got some solid that's described as the cylinder x squared plus y squared equals 1, below 4, so only going up as far as z equals 4. But instead of the base being at z equals 0, we're going to have the base be formed by the parabola z equals 1 minus x squared minus y squared. This picture gives a rough idea of what's going on. Obviously, I didn't draw the axes in because it would have been disastrous. But here is the xy plane. Here's z equals 0. Here's z equals 4. The z-axis would be, the z-axis would be cutting right through the middle of this shape. So here you can see essentially the idea is, instead of this just being a cylinder, the bottom of the cylinder is kind of caved in. So, and let's go a step further and suppose this has a density of the square root, a density in terms of its mass, so that we're actually taking the integral of something. Remember that one of the ways we can think about actually taking triple integrals of a function in terms of physical attributes is we could think of f of x, y, and z as kind of a density with respect to x, y, and z, and then what happens is the integral gives us its total mass. That's a reasonable idea of how you can think about triple integrals of an actual function instead of just triple integrals to make a volume. There are plenty of other interpretations, but that's one I find helpful. It can also just interpret a volume in 4 dimensions if you want, but I don't know about you, but that's hard for me to picture. So let's go ahead and actually see what happens here. We can do this in a couple of different ways, and the one I'm going to show initially is we're going to integrate with according to z ahead of time, and then once we've done that, once we've gotten this down to 2 integrals, then we're just going to convert to polar, and we'll see that this is going to work fine. So here, what we do is we say, hey, z needs to go from 1 minus x squared minus y squared to 4. So that's what we're integrating here, and we're integrating the square root of x squared plus y squared, and that just means that when we integrate it, we just get z times the square root of x squared times the square root of x squared plus y squared, and this just becomes 4 minus 1 minus x squared minus y squared. But now this is no good. This is not a helpful integral anymore. So now we can convert to polar. And here what happens is we say, okay, great. 1 minus x squared minus y squared becomes 1 minus r squared. Not a problem. The square root of x squared plus y squared just becomes the square root of r squared, which is r. And the region that we're looking at is just the circle with r equals 1. So r is between 0 and 1. Theta is between 0 and 2 pi. Polar coordinates in the polar integration in the normal sense. So here we're going to switch this. We're going to complete our switch to polar. 4 minus 1 minus r squared becomes 3 plus r squared. R times r dr d theta becomes r squared dr d theta. So we have the integral from 0 to 2 pi, 0 to 1, 3r squared plus r to the 4th dr d theta. If we deal with r first, we get r cubed plus r to the 5th over 5, evaluated from 0 to 1, which becomes 6/5. So we get the integral from 0 to 2 theta of 6/5 d theta, which is, I think, quite clearly 12 pi over 5. And we're done. This is if we're talking about, this as being as we're talking about our function as being a density, then this is the mass of this cylindrical-ish shape of this, caved in cylinder. And we're good. Done. Note, we actually could have converted to polar ahead of time and made z just be in terms of r and theta right away. Instead of z being a function of x and y, we could have made it a function of r and theta, and it just would have, and in fact, just a function of r in this case, just a function of r, here at least. And so what we get is z equals 1 minus r squared, as we already saw. So instead, we might have this integral, and we would just convert everything ahead of time. And this will come out and this integral will work out exactly the same way. Here you can see the integral for theta is the same, the integral for r is the same. Z became, instead of 1 minus x squared minus y squared, it became 1 minus r squared. Still goes to 4. The square root of x squared minus y squared became r, and we've already converted to polar, so that means dA had to become r dr d theta, and dz just stayed. This is exactly the same integral. It will work out to exactly the same answer. So yeah, this is it for cylindrical coordinates. There's not really, in my opinion, a lot here. Cylindrical coordinates are generally just, you see you have a cylinder, you see that you're describing your shape with a cylinder. That's just default switch to cylindrical coordinates. Or if your projection onto, if your projection onto the xy plane, or if you're dealing with a different type of integral, you might change y and z to r and theta and leave x alone. Like that, that's also fine. There's nothing wrong with doing that. Everything I'm going to ask you is going to be a triple integral of the first type. So something where something where x and y would be the thing, would be, would be kind of what we're projecting onto. Would the xy plane represents our d, if you will, and the z plane represents kind of or the z axis rather represents what's just going to be our height, or represents the first integral that we're taking. I mean, z is always the height, but represents the first integral we take. The function most likely to be in terms of x and y. So, or in terms of the other two variables, if we're going to be general. So generally, if what you're projecting onto is best represented in polar form, but you would like to leave your height as is, this is a good choice for cylindrical, and often that's a case where we're inside or outside a cylinder. So next up, we'll take a look at the, in my opinion, more difficult integration in spherical coordinates, and more difficult because not because the integrations themselves are any more difficult. I mean, it's still just an iterated integral. But because spherical coordinates, in my opinion, are horrible. I personally just don't like them. Unfortunately, or if you happen to like them, or if you're not like me and have no problems with them, then fortunately or neutrally, they matter. We do need to know how, we will sometimes need to use these. It took me personally a very long time to get my head around it, but that's not the same for everyone. So when we talk about spherical coordinates, recall that the conversion to spherical is x is equal to rho sine of phi cosine of theta, y is equal to rho sine of phi sine of theta, and z is equal to rho cosine of phi. Hopefully you recall at the beginning of the semester us talking about how these conversions happen, like the actual way that we see these happen. I don't want to spend time in this lecture going over that right now. But recall that in the case of spherical coordinates, we have no particular conditions about theta beyond that it's somewhere between 0 and 2 pi. Rho needs to be greater than or equal to 0. Phi needs to be between 0 and pi, because phi is representing the angle from our positive z-axis, so it's only ever going to go as far as the negative z-axis. Theta represents the angle of rotation around the z-axis. Rho represents our distance from the z-axis, or from not the z-axis, sorry, but the origin. A side note here, and I forgot to put it in my original notes, so you can see it's written in computer pen. It's written in editing pen, in the PDF pen. There we go. That's what I was looking for. Is that if we somehow need to bounce between the polar r and spherical coordinates, r is equal to rho sine of phi. As a side note, by the way, I've heard students pronounce phi as phi. Linguistically, that's actually probably correct. I believe Greek pronunciation would be phi, but then Greek pronunciation of pi is p. So unless you're planning to start talking about the area of a, the area of a circle being, PR squared, it's phi. Any mathematician you ever talk to says phi. So, it's, yeah, you can say phi, it's not wrong, but it's phi. All right, sorry, random aside. You can ignore that last 30 seconds. All right. So, talking about how we form the Riemann sum for spherical coordinates. We're going to talk about it in the same way that we talked about the Riemann sum for polar coordinates. Or not the Riemann, the small the small little, like, differentiably small segments that we look at. In this case, not not necessarily a small rectangle or a small piece of a polar crosshatch like we saw before, but this time a very small little chunk of volume. So, first off, what we have here is, I've tried my best to draw this, and I'm going to try and explain how things are coming around. This is our shape. Assume it's very, 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 very magnified. So the angle that this shape takes up when projected onto the XY plane, its angle is projected down here, and that angle is d theta. It's a small change in theta. That's very direct. There is no surprises here. If we want to know what the if we want to know what exactly the length of this particular segment here is, even though it's an arc, we're just going to say that it's rho d phi. And the reason that this is just rho d phi, is that phi represents our angle from the z-axis. And obviously rho represents our distance from the z-axis. What we make here is we say that this is a similar triangles argument, essentially saying that d phi represents represents a minuscule change in phi. So just the actual change of angle, like down here, which I haven't drawn in, but the change of angle down here would be d phi. So what ends up happening is, by a similar triangle argument, because we're going to treat this like it's a triangle, even though obviously it's an arc. It's so small that it can be treated like a triangle. It's the same argument we made for polar coordinates. So here, because this change in angle is d phi, the actual length of the shape is rho d phi. By a similar triangle argument. And we're going to make the same argument here for the depth of this particular shape. And once again, it's going to be rho, but now it's going to be sine of phi d theta. And the reason that it needs to be sine of phi d theta, or more specifically rho sine of phi d theta, is that this length simply represents the length projected onto the xy plane. So what it really needs to be is r d theta, in the same way that it was for polar coordinates, where essentially d theta represents this, but if we actually want a length, it's r d theta. So here, what ends up happening is, we say, okay, well, this length is r d theta, but r is rho sine of theta. So rho sine of theta d theta. And then finally, the actual, like, length of this shape, so from here to here, here to here, is just d rho. There's no surprises there. So what we end up with here is a volume, if we kind of multiply these things together like it's a box, again, length by width by height. Again, we're making the argument that there's not really a problem in doing this, because this is such a small shape that even though it's not a box, it's so close to a box that we're going to treat it like one. So this just becomes rho sine of phi d theta times rho d phi times d rho. And otherwise, and then multiplying this all out, we get rho squared sine of phi d rho d theta d phi. So this is, instead of dv, this is our new breakdown of what we need to, of our essentially this is going to be the results of a three-dimensional Jacobian. We'll come back to that soon. But this is going to be our new, our the new thing we need to multiply by. And then, this is, in no particular order, our variables of integration. All right. So generally, we are using spherical coordinates for things like spheres and cones. This should make sense that you would use spherical coordinates for spheres. A lot of times that means we're going to define most of our boundaries with constants. That's good. That makes life easier. In the case where everything's defined with a constant, so this would just be on a sphere without any particular other controls you need to make, like just dealing with regions in a sphere. We might say that rho is between two constants a and b. We might say that theta is between two angles, alpha and beta, and we might say that phi is between two angles, gamma and delta. I just went with Greek letters in order. Don't look too far into that. So what we have here is something simple where we would just say, okay, here are our boundaries. We still, when we actually change to spherical coordinates, we need to multiply by rho squared sine of phi, and then we can, have d rho d theta d phi. And then f wouldn't be f of x, y, z anymore. It would become f of rho sine of phi cosine of theta, rho sine of phi sine of theta, rho cosine of phi. Quite the mouthful. And a lot of times the things that's going to make changing to sphere, there are two things that are going to make changing to spherical coordinates be a problem. One of them is going to be figuring out what your boundaries are, because it's not something that we often practice prior to this course. Thinking about shapes in polar or spherical coordinates, certainly not spherical coordinates, and even polar, not so much. And what that means is that it can be hard to come up with boundaries, and it just takes practice. And I'll tell you right now, drawing shapes helps, man. So yeah, the boundaries, coming up with your boundaries will be one thing, but in the end, you're just still trying to say, like, okay, if I convert to spherical coordinates, what does this look like? And if I'm supposed to be between two shapes, or if I'm supposed to be between two surfaces, what's the smaller surface, what's the larger surface? So if rho is supposed to be between two surfaces, which one is closer to the origin? Which one's further from the origin? There are your boundaries. If I'm trying to put phi between two angles, between the starting angle and an ending angle, which angle which angle has to travel less far from the positive z-axis? So like it's doable, and just the way that we're going to do these is by taking all of our x, y's, and z's and converting them to spherical. And the other thing that's going to be a pain is sometimes if you have a complex function here, it's not usually it might not get better if you're making these conversions. The good news is that often the whole point of switching to spherical is if you have a function that makes more sense in spherical coordinates. So it actually might get better. And we'll see an example of that coming up very, very shortly. So for the record, last thing, if we did have functional boundaries, we might say that rho is between some function g sub 1 of theta and phi, and less than some, and between something where it's less than some other function g sub 2 of theta and phi. We might say phi often, theta and phi will both be between two known angles. It is certainly possible to have phi be a function of theta or vice versa. We're not going to be looking at problems that deal with that. That's we're not going to contest. We're not going to deal with that. So generally those are not common. Those are not shapes that are formed by anything other than like just drawing some arbitrary arcs. Most of the shapes that we care about, most of the things that we'll look at, theta and phi will be between constants. Rho might not be. Rho might be between functions. So let's take a look at an example. And this is going to be something where exactly rho will be between functions, but theta and phi will be between constants. Rho will actually have a more formal function. So let's find the volume above the cone. Z equals the square root of x squared plus y squared, but below the sphere, x squared plus y squared plus z squared equals z. The sphere, I didn't draw this, and I did not prepare an image online. So I'll, if you're curious, I encourage you to check this out yourself. Feel free just to Google 3D graphing, and you'll get, pick the first site. But as a rough pick, this cone z equals the square root of x squared plus y squared. That's just a cone going the cone specifically above the with its point on the origin and extending upward, going out at an angle of pi over 4, or an angle of 45 degrees. The sphere x squared plus y squared plus z squared equals z. If you were to take a look at kind of what's going to result from this, what you end up having is that this is just going to be this is just going to end up being the sphere, where it's a sphere of radius 1, radius 1, but shifted upward by 1 unit. So its center is on z equals 1 instead of z equals 0, and everything else is the same. So what we get here is rather, sorry, its radius is 1/2, not 1. My apologies, and its center is on z equals 1/2. My apologies. So what we have here is we get rho squared equals rho cosine of theta by plugging in spherical coordinates. We're dealing with a sphere, so let's try spherical coordinates. And x squared plus y squared plus z squared equals rho squared. Z equals rho cosine of, I said theta there, I mean phi. Z equals rho cosine of phi. So what we get is rho squared equals rho cosine of phi. In other words, rho equals cosine of phi. And this is going to be our boundary for rho. This is as far as rho is going to go. Rho will go no further than cosine of phi, because if we did, we'd be outside the sphere. So rho goes from 0 to cosine of phi. Easy enough. We already discussed that this cone, z equals the square root of x squared plus y squared, is the same as saying that we get an angle, that it's a cone with an angle that's pi over 4. So what that means is that our cone will extend no further than pi over 4 from the positive z-axis. So in other words, phi goes from 0 to pi over 4. You can see I actually, rather than just kind of knowing what this cone looks like, you can see that you can actually perform the arithmetic here, and you can convert to spherical and then actually see what goes on. you get rho cosine phi equals rho sine phi. Cosine and sine are only equal from 0 to pi, at least, at pi over 4. So that must be the boundary for phi. And obviously phi starts at 0 because we're looking at, of the region in, positive coordinates, or in positive z at least. And then finally, it's the full, it's the full rotation around the z-axis. It's the full cone. It's the full sphere. So theta just goes from 0 to 2 pi. So those are our boundaries. And our function, well, we're looking for a volume. So there is, the function's 1. So when we make this conversion, we get our boundaries, rho squared sine of phi d rho d phi d theta. And now we just integrate. Rho squared, when we integrate it, becomes rho cubed over 3. So it becomes cosine cubed of phi times sine of phi over 3. Integrate with respect to phi. Well, the easiest way to do this is just make a u substitution where we say, u is cosine of theta. If we do that, what we're going to get is negative cosine to the 4th of phi, or cosine of theta, sorry, cosine of phi. Negative cosine to the 4th of phi over 12, because after integration, we would have u to the 4th over 4, times 1/3. And we evaluate this from 0 to pi over 4. Cosine of pi over 4 is equal to root 2 over 2. So what we would get here is ultimately cosine to the 4th is going to be 1/4. So we'd have negative 1/4 times 1/12, so negative 1 over 48 minus negative 1 over 12. Cosine of 0 is obviously 1, so just 1/12. So what we end up getting here is 1/16. And then we just integrate that from 0 to 2 pi d theta, and we just get pi over 8, and that's our answer. And this is it. So the thing to notice here is that the hardest part of this entire problem is the trig, right? The hardest part was making sure that we didn't make mistakes in setting up what we are actually trying to evaluate. So all we have to do from from this point forward is just say, all right, we can we can go ahead and just say, well, I'm perfectly happy to just take a look at what I need to do in terms of another problem. I can we can go on to another example. I kind of lost my train of thought there. I'm sorry. So yeah, sorry. Back on the correct train of thought here. All we have to do here is just make sure that when we make these conversions, if worse comes to worse, just try and convert directly. If you can picture shapes, if you can make the obvious, if you can see kind of what the shapes are going to be, that might help you out. But if you convert directly, algebraically, you'll always be able to resolve things. You just might get stuck with sometimes needing to be a little clever with trig. Also, sometimes in the integrals themselves, you'll need to use some trig identities in order to make these integrals work out nicer. You'll have integrals of cosine and sine an awful lot. So knowing your trig identities can be important. So let's take a look at one more example, and we'll call it. So let's shift to. Actually, we're going to shift to this. I'll show kind of the idea of what I'm looking at right away. What I want to look at is I want to look at the region that is between the cone z equals negative square root of 3x squared plus 3y squared and the sphere x squared plus y squared plus z squared equals 16. I would like, this is my region E. so you can see, you know, you can see what this looks like. This is one I prepared so we can actually see it. So, you know, this region in here, kind of like an upside down snow cone. All right, so let's talk about what it is I want to integrate, because what we're going to say is that I'm actually going to take this a step further and say that specifically I want to integrate the function z cubed. So you know, my density is, you know, whatever my density is going to be equal to z cubed. So let's take a look at what we're going to end up getting here. So first things first, we are going from zero to we are going from 0 to 4. Let's take a look again at our you know, two functions here. We have x squared plus y squared plus z squared equals 16. This tells us that rho squared equals 16. In other words, you know, our outer boundary is that rho equals 4. We get this right away. The other thing we were looking at is z equals negative, there should be a negative there, 3x squared plus 3y squared. And x squared plus y squared is the same as r, but we've already said that, you know, recalling that r is supposed to be rho sine of phi. That's an awful phi. Better. What we're going to get here is that z is going to be equal to, and keep in mind, z is rho cosine of phi. We're going to get that rho cosine of phi is equal to negative root 3 times the square root of r squared. So we're going to get negative root 3 rho sine of phi. And what this ultimately means, if I divide, you know, if I kind of isolate my phi, if you will, or if I try and get my trig functions on one side and everything else on the other, is I'm ultimately going to get that tangent, oops, not that, not inverse tangent. Tangent of phi is equal to -1 over root 3. And this is true for phi between 0 and pi, at least, at 5 pi over 6. And based on the shape that we're looking for, what we're going to get is that phi needs to be between 5 pi over 6 and pi. Rho needs to be between 0 and rho needs to be between 0 and 4. And then lastly, the only thing that we haven't written yet is what's going on with theta. But we're, again, this is a sphere and a cone. There's no particular boundaries for theta. So theta just goes from 0 to 2 pi. And lastly, this z is the same thing as rho cosine of theta, or rho cosine of phi. So we get rho cubed cosine cubed of phi for z. So what we end up having here in terms of our integral is, and you're going to have to forgive me here, I'm going to have to clear things so that we have room. What we end up having here for our integral is going to be this. We're going to have the integral from 5 pi over 6 to pi. That's definitely a pi. Shut up, it is. The integral from 0 to 2 pi, and then the integral from 0 to 4 of rho cubed cosine cubed of phi. Let's pretend that's a phi. And then what we're going to have is times rho squared sine of phi, and then d rho d theta d phi. So this is the integral we're looking at. Now integrating with respect to rho is relatively easy. We can do that one pretty much for free. What we're going to get is rho to the 6th over 6. 4 to the 6th is 4,096. Don't ask why I know that off the top of my head. Powers of 2, baby. So we're going to get 4,096 over 6, which is the same as 2048 over 3. So we get 5 pi over 6 to pi. We get, that's an integral. We get 0 to 2 pi here. And then we've just got, 2048 over 3 cosine cubed of phi sine of phi d theta d phi. That's a phi, not a rho. And now again, it's not really a problem to be it's not really a problem to integrate with respect to theta. That's very, very easy. There's no theta here, so it just becomes all this times theta evaluated from 0 to 2 pi. We can pull our constant. At this point, I'm going to pull the constant out. It's just 2048 over 3 times 2 pi. So we're back to 4096. And that's just going to be 4096 pi over 3 of the integral from 5 pi over 6 to pi of cosine cubed of phi sine of phi d phi. That's the best phi I've drawn so far. It's the only good one. So here we just make a u substitution, right? Pretty simple u sub. We get, u is equal to cosine of phi. So what we end up having here is, if we, find our, du d phi, what we end up getting is, negative, sine of phi, and we can just go operate from there, correct? So all said and done, if we kind of go through the complete process of our u substitution, what we're going to get is we're going to end up getting an extra negative in here, which we'll go ahead and factor out. So we'll get negative 4096 pi over 3. Then we'll have what looks like cosine to the 4th of phi over 4 evaluated from 5 pi over 6 to pi. Obviously, this 4th can cancel with that 4096 and just become 1024. And what this means is we're going to get negative 1024 pi over 3 times cosine of pi is just -1. -1 to the 4th is 1. Amazing. Let's make that less like a, strange thing and more like a 1. And then 5 pi over 6, cosine of 5 pi over 6 is -√3 over 2. -√3 over 2 to the 4th is 9 over 16. So we get 1 minus 9 over 16. So in other words, we have -1024 pi over 3 times 7 over 16. So, the over 16 is easy enough. That's 64. 64 by 7. This is where I regret not doing these problems ahead of time. 448. So we end up getting -448 pi over 3. And this should fit because as a volume, obviously things would be positive, but we weren't looking at a volume. We were looking at the signed mass, if you will, of something where we're going from z equals 0 to z equals, some negative, going downward. If we go back to our original picture, this is a shape below. This is a shape involving, negative z, and that was what we were basing our basing our function off of. And since we were to a third power, negative signs are going to remain. So we'd expect our answer to be negative. So, that's why we get a, if we're thinking about this as a mass, that's why we get a negative mass. It's where that kind of falls short. So yeah, this is kind of what goes into our work. This is what we need to do. And this is about as difficult a problem as I'm going to ask you. I'm really not going to try. My goal is not to make spherical coordinates be horrible and painful. My goal is for you to understand how they're used. So yeah, until next time.